Okay, so we're going to talk about strings and specifically talking about strings, comparing strings for different string instruments, somewhat along the lines of Jim's talk. I'm not going to concentrate too much on or really talk about different strings for the same particular instrument, but compare um, strings for different instruments. Hold on a sec. I need to bring up the participants list so I can mute people. Okay. All right.
I'll keep
Um,
an eye on that as well, Fan.
oh,
Sorry.
great. Thank you. Yeah, because I've given you co-host privileges. So why do we use strings? Well, there are different ways of generating musical sounds, and strings are one very practical way to generate distinct tones for a musical instrument. And one advantage of strings is that the pitch can be changed relatively easily by changing the properties of the string. For example, you can change the vibrating length by changing by stopping it with a fret or with a finger. And you can change the playing tension of the string with the tuning peg, and then that will also change the frequency, the vibrating frequency of the string. Now, presumably the first string instrument probably had only one string. We call that a monochord. But then someone probably figured out, oh, there's some advantages of adding more strings. So it's obvious that you can cover a much wider range of frequencies with multiple strings without having to travel large distances up and down the string, with your fingers to stop the string. Also, another advantage is that the higher pitch notes, if you're playing very high pitch note on one string, the notes are crowded very closely together. And now we have amazing virtuosos that can do that very well, but for most of us, it's very difficult to play very high up on the string. And there's the ability to play chords, of course. So now, historically, the frequency of the highest string on a multi-string instrument has been set by the breaking strength of the string material. And the most common string material was gut, typically the small intestines of sheep. Now, today we have modern materials, and so we have higher strength materials, so we can actually go higher in frequency than the traditional tunings, and people do. On the low end, the bottom string, the lowest frequency of the instrument, it's usually set by the acoustical limitations of the instrument body. Because as you get lower and lower in frequency, it radiates much less effectively. Again, in our modern world with electronic amplification, you can go much lower in frequency than traditionally. And so there are a lot of people doing precisely that. They're making, for example, octave violins, violins that play one octave lower than your traditional violin. And it poses some very challenging challenges for the string designer to make what are essentially cello or even bass strings function on a violin. So what is a musical string? Well, it's a thin, long, uniform, and flexible structure of a finite length that vibrates with a distinct single tone. And so that sort of defines a somewhat ideal string. And you'll find ideal strings in textbooks. And so what's an ideal string? Well, it's perfectly uniform. Because if it's not perfectly uniform, it will not vibrate the way you expect it. The good news is that modern strings are very uniform using modern technology. That wasn't the case with gut strings. For those of you who are my age and older, a little older, I grew up on gut strings. And I remember that because it's a natural material, every once in a while I would buy a gut string and it just would not vibrate at all under bowing. It would just go squawk. And that's what was traditionally called, a false string back then, a really false string. Ideal strings are also perfectly flexible. And we'll talk a little bit about this next, which is that real strings are not perfectly flexible. They have bending stiffness. If you try to bend a real string, it resists bending. And one of the main effects of that is that the higher vibration modes of the string with bending stiffness are sharp relative to harmonic. There's lots of other little things about strings that are very important. We'll mention them in passing throughout this talk. So, all structures will vibrate at multiple and different frequencies, but typically those frequencies have no simple relationship to each other. Turns out, though, one of the exceptions is an ideal string. An ideal string, a distinct single tone is possible because the string vibrates harmonically. That is, all of its higher modes of vibration are exact integer multiples of its fundamental frequencies. And when a string vibrates harmonically, the ear tends to identify the fundamental frequency of that string as the source of a single distinct pitch. So, what can I, as a string designer, control? Well, there's some easier stuff. Playing tension. We'll talk about that in this talk. Damping. We'll also cover a bit of that in this talk. Some harder stuff to control is bending stiffness. We'll also cover that. I'm going to ignore all the hard stuff. Things like damping behavior that varies with amplitude, the effects of core elasticity, torsional stiffness, the effects of different materials and winding geometries and string constructions. All those factors in engineering terms are fairly small. They're equivalent to all those differences, between measurements of different guitars or violins or beer cans that you saw in Jim's talk. But those small differences are really important to the player. But I'm going to ignore them for the talk because it's hard to model them and fully control them. Also, those things are irrelevant if we can't get the easier stuff correct first, which is playing tension, damping, bending stiffness. All right, so we first have to build a string that actually, it's sort of like, okay, you have to be able to build a structure that actually sounds sort of like a violin before you can start optimizing the little details of the violin. You don't want to end up with a guitar if your goal was to build a violin. So let's start with bending stiffness. So what are the effects of bending stiffness? Well, one of the main effects is that it increases the damping. And Jim and Nicholas, who's also on this talk, they've written a paper that they've published recently. It's on their website and explains this very well. And so bending stiffness will increase damping and it leads to a less bright sound. Also, because the string is not vibrating harmonically, it may not sound exactly in tune when plucked, okay? Typically, it's not an issue when the bending stiffness is low, but if the bending stiffness is really high, it may start to play a role. And for bow string applications, it makes it much harder to start a string vibrating with a bow. So let's talk a little bit about that, cover it. And for that, we have to know a little bit about how bow strings vibrate, because a bow string vibrates very differently from a plucked string. And so the bow string vibration is called the Helmholtz motion after the German scientist who first discovered it, or it's called stick slip. And here's an animation that I got off the internet. So the bending stiffness of the string causes the string higher frequency modes, musicians call them overtones, to be sharp relative to the harmonic, as I've mentioned before. However, the Helmholtz motion, the bowing motion, forces the string to vibrate harmonically. So if the string doesn't want to vibrate harmonically on its own, it's hard to bow. It's hard to get the string started with the bow. So that's one of the main effects of bending stiffness on bowed strings. So now, how do we control and minimize bending stiffness? Well, the main way we do that is we wind strings. And actually, that's what most string companies, the major thing we do is, if you come and visit our factory, you'll see dozens and dozens, hundreds of winding machines. So you'll see there's a picture of a guitar winding machine on the left and an orchestral bass winding machine on the right. So now as the string gets larger and larger in diameter, we also make use of multiple windings, different materials, geometries, and all in an effort to reduce the bending stiffness. Historical gut strings also use another technique, which is to twisting the gut to reduce bending stiffness. So the challenge is, well, you can reduce the bending stiffness, but there's another important factor, which I'll just touch upon, which is torsional stiffness, which is the ability of the string to resist twisting as it's either plucked or, more importantly, in bowing applications. Structures that have very low bending stiffness typically have low torsional stiffness as well. What we want in a string is generally to have low bending stiffness, but high torsional stiffness. And those two things are very difficult to get at the same time. And so string design, one of the main challenges of string design could be reduced simply down to how do you reduce bending stiffness, but increase torsional stiffness at the same time. It's not easy. I'll comment on the pictures that you see. If you look very carefully at the picture on the left, you'll actually notice that there are actually 3 winding machines stacked on top of each other. And one operator is actually operating all 3 machines at the same time. Now, people often wonder, for example, why are orchestral strings so much more expensive than guitar strings? Oftentimes, you can buy a whole package of guitar strings for the price of one orchestral string. Well, the main reason is that orchestral strings are much more complex, typically have much more winding layers than guitar strings. And we can make guitar strings about an order of magnitude faster than we can make orchestral strings. So a guitar string could, come off the machine in anywhere from 10, 20 seconds for a string, but it may take us several minutes to make an orchestral string. Next, let's look at string tension. So the string playing tension is the force along the length of a string after it's tuned up. And we control string tension through the string mass. If you work out the vibrating string equation, you get a relationship where the tension is proportional to the frequency squared, the length squared, and the unit mass. Now, the frequency and the length, in this case, are the inputs or the constraints to the system because they're defined by the instrument. So we control tension directly through the unit mass. So if you want a higher tension string, you put more mass on the string, thicker windings, more windings, or a higher density material. What are the effects of string tension? Well, if you have a higher string tension, it exerts more force on the bridge as it vibrates, which gets transmitted to the body of the instrument, and it should, all else being equal, produce more sound. Now, this is the dynamic vibrating force. I'm not talking about the static force exerted on the top of the bridge on the top of the instrument and its effect, which Joseph Curtin will talk about in the next talk. Okay. A higher tension string, it's harder to pluck because as you displace the string, it resists. I mean, that's actually the tension of the string. There's a little geometrical factor. You use your high school trigonometry, and that's actually the restoring force of the string, and that's what causes it to vibrate. Also, a higher tension string is just harder to bow. We'll cover a little bit of that later in the talk. So, we string manufacturers, we make strings with different tensions and gauges to allow finer control over the sound and response. So the problem, though, is that there's no optimal tension, single optimal ideal tension, because it depends on the player and the instrument. There are no standards for a so-called, let's say, medium tension string set. Every manufacturer has their own standards, and even different brands from the same manufacturer may have different tensions for what's the so-called medium set. Now, in practice, the medium tension set in the orchestral bow string world, the medium tension set is what the manufacturer has determined would work best for the majority of instruments and players. And in most cases, 80 to 90% of the strings we sell are the medium tension version. But we do make light and heavy tension versions because specific strings may, an instrument or player may desire a higher or a lower tension. And specific strings on an instrument may actually benefit from a higher or lower tension than their neighbors. So some people will use, let's say, for example, a higher tension G string. One of the most popular traditional sets of orchestral strings out there from many years ago actually had a fairly low tension G string. So it's very popular to use just a higher tension, heavy tension G string while using the medium tension for the rest of the set. So there's room for experimentation there and optimizations. Now, we and several other manufacturers have tension data for all of our strings on our websites, so check it out there. So now I want to talk about typical string tensions for sets of strings for different instruments. Let's compare them and see what insight we might gain into strings and the instruments themselves. So here are some typical bow string tensions of typical sets. Okay, the absolute numbers are less important than sort of the trends that we see. A couple of apologies are in order here. Number one, I couldn't figure out how to get the tension in metric units. On the right-hand side, I'm used to using tensions in English units, so that's the way I've plotted it. And yes, the basses are tuned in fourths, not in fifths. Well, the rest of the instruments are tuned in fifths. So it's not exactly a one-to-one correspondence, but the general trends are still valid. So one of the things we notice is that the tensions are higher for larger, lower frequency instruments. The trend is very clear. For the violin, viola, and cello, it's also very clear that the first string of those instruments are much higher tensions than the bottom strings. And this, I think, is a fairly recent historical development. And I think it's due to a combination of factors. First of all, the use of all of these instruments, and not just the violin, but especially viola and cello, which were traditional ensemble instruments, but the rise of those instruments as solo instruments, and the use of the top strings of any of these instruments as sort of the most powerful solo projecting string. Another factor in this is that the development of very high strength steel wire has allowed much higher tension for strings on these instruments. Remember, the traditional limitation on tensions on these instruments and tuning, well, it's mainly tuning, was the material of the gut. And so if you started using much higher tension gut, there's actually a trade-off because with bending stiffness. And so even though the stress is the same for the same tuning, there's all mathematical stuff you work out, it turns out typically in practice, larger diameter strings are actually less strong than the smaller diameter strings. And so the third factor, I think that's very relevant, especially for viola and cello A strings, the top strings, is the development of very effective damping materials, which we'll cover a little later, which allows very high tension strings to be used without those strings sounding overly bright. So modern cello, viola, violin first strings are almost predominantly use solid steel wire cores nowadays. So this is very different than, let's say, 100 years ago, which was still gut. So the steel wire allows much higher tensions to be used for those strings. Now, for the bass, it's a little different. It's actually the opposite. You see that the string tensions increase with the lower frequencies. It's probably to compensate for the decreased output of the bass at the lower frequencies. And for the bass, it's the low notes that are the most important. And I put in electric bass guitar strings in there because they're tuned exactly the same as an acoustic bass, although the string lengths are just a little shorter, but they're not. It's not different enough to affect the trends here. If you look at electric bass guitar strings, the tensions actually decrease as you go lower for the bottom strings. And I think that's due to a couple of reasons. Number one, electronic amplification. You don't need more output, at least from the string or the instrument body itself at the lower frequencies, because with electronic amplification, you can deal with that very easily. Also, it makes it easier to pluck the lower strings because the typical electric bass strings are made from solid steel cores. And the cores for the lower strings are typically larger in diameter. And those very large, thick steel cores adds an additional restoring force as you stretch a string due to longitudinal stiffness. And so it just makes it harder to pluck if you had really high tensions for the lower strings. So I think they reduce the tensions for the bass guitar strings for several reasons like that. So here are some typical guitar string tensions. Again, plotted as a function of the string. And so this is sort of interesting because classical guitar strings use gut. That limited string tension is actually due to high bending stiffness if you go really large diameter gut. And it determine a particular style of playing that's, the classical style of playing for classical guitar. Now, modern classical guitar strings use monofilament polymers, typically nylon, for the upper three strings, and multifilament synthetic core wound lower three strings, typically wound with silver plated copper. The third string of a classical guitar is not entirely satisfactory due to the high bending stiffness. It's a very large diameter nylon monofilament. But typically, classical guitar players do not want to use a wound third string because it probably would sound too different from the top two monofilament nylon strings. So they put up with a monofilament nylon third string. Now, I would mention that there are now new materials that allow a slightly smaller diameter and therefore lower bending stiffness third guitar string, and they're gaining in popularity. Now, let's look at the acoustic guitar. Actually, I should probably use my pointer, laser pointer. There we go. Yeah, so acoustic guitar has about twice the playing tensions of a classical guitar. Now, they need much more acoustic output. If you've ever gone to a classical guitar recital or concert, you realize how soft they sound. And in fact, some of those concerts I've gone to in a large hall, they actually use amplification, electronic amplification. But without electronic amplification, classical guitars sound really soft. They're not loud. So acoustic guitars, to get more acoustic output, they've boosted the string tensions, and it's made possible by modern steel cores, steel, typically brass alloys wound on steel cores. So with the higher tensions and the larger diameters and the use of metals, which are not as flexible as synthetics, turns out that the third string of an acoustic guitar needs to be wound. Otherwise, the bending stiffness is too large if you use a plain steel string for that. For electric guitar, well, you have the benefit of electronic amplification. So you don't need such high string tensions to produce more acoustic output. You can just turn up the gain on your amplifier. So you can see the electric guitar string tensions are much closer to classical guitar string tensions. Furthermore, because of the thinner gauges, the third string can use a plain unwound steel string. That's fairly standard. For electric bass guitar, well, they're all wound, of course. We've sort of touched on those strings before. Let's go to something a little more technical. Impedance. So if you want to know something about the properties of a vibrating system to predict its behavior, you need to know something about its geometry, its mass, its stiffness, its damping. In general, you need to know both the mass and stiffness. And the impedance is a very useful concept because it encapsulates both the mass and stiffness into one number. And it measures how much a structure resists motion when subjected to a force. Technically, it's the force divided by the velocity. It's also the reciprocal of the admittance mentioned in Jim's talk. This is one of the problems. Some people use impedance, some people use the reciprocal admittance. Here I'm using impedance. So for a string, so the mechanical impedance typically is proportional to the square root of the mass times the stiffness. And for a string, the mass is the mass per unit length, and the stiffness is the tension of the string. That's what provides a restoring force for the string that allows it to vibrate. And if you work out the math, and the string impedance is proportional to the tension divided by the length and the frequency. So for string, because the length and the frequency are the inputs, those are the constraints, the tension uniquely determines the impedance. Okay, so for strings, we can, if for a given string of a given length and frequency, if we know the tension, we know the impedance. So now, if you look at that bottom equation, what about strings for different strings on the same instrument? Well, you see that for the lower frequencies, if you have roughly the same tension, the string impedance goes up. Okay? If the tensions are roughly equal. Now, this concept of impedance or admittance in Jim's talk is important because strings actually work in conjunction with the instrument, at least acoustic ones. Electric guitar is the exception, doesn't really have a radiating body. So larger instruments typically have more mass. They have thicker plates, which are stiffer. So you would expect them to have higher mechanical impedance. And probably all else being equal, you would expect their strings to have higher impedance. And guess what? They do. And so this is basically the plots of the same strings that I showed earlier of string tensions. These are the impedances of the strings. So we see a general trend of increasing impedance with the lower strings. This is for orchestral strings. This is for guitar strings. So, as I said before, we expect larger instruments to have higher mechanical impedances in general, although the actual impedance depends on the frequency, and it's highly complicated, as was shown in Jim's talk, but we're just talking about overall general trends. So one of the interesting questions that rises from this is, well, should you be designing strings with equal tensions or roughly equal impedances across a set of strings, or neither? Well, let's look at the advantages and disadvantages of each. Now, if you have roughly equal string impedances across the set of strings, perhaps it might match the body impedances better. The main downside is that it results in an extremely uneven string tensions. And you have a playability problem. As I've mentioned before, I talked about the playability. If the string tensions are highly unequal, the feel to the player in a plucked situation is very uneven. And even for a bowed application, the deflection under bowing is going to be very different. And so that leads to playability problems. So a roughly equal string tension leads to a much more uniform feel for both plucking and bowing, with one exception I'll mention a little later. So this leads to sort of my hypothesis. Well, string tensions are set mainly by the maximum tension for maximum sound output that feels comfortable to play. Hopefully that doesn't sound too controversial. In reality, modern string sets are neither equal tension nor equal impedance, but they're actually closer to equal tension. As I said, it leads to a more uniform feel in plucking and bowing. The other consideration for bowing is that the minimum bow force depends on the impedance, not on the tension, actually. Which means that if you have a roughly equal tension set, the minimum bow force increases for the lower strings. Now, the problem with a roughly equal impedance set is, as I said, either the lower strings would feel too loose and floppy under bowing, or the upper strings would have excessively high minimum bowing forces, where playing fast notes are more important. That's in theory. In practice, it actually works out pretty well, because let's go back to the string impedances for violin and viola, especially. And we see that actually you can argue for the top three strings of those instruments, they're roughly equal impedance. Well, one of the main reasons is now the advent of a super high tension first string, made possible by modern string technology. So for violin, viola, cello, it's sort of quasi roughly equal playing tensions for the bottom three strings and sort of roughly equal impedances for the top three strings, you can sort of argue. Because for the bass, you can see that the string impedances increases dramatically as you go lower. And for plucked instruments, you see the same trend. So now, one of the downsides, of course, of having a dramatically increasing impedance with a bowed bass string is that the bottom strings become harder and harder to bow because the minimum bow forces increases with the string impedance. And so in general, yes, that's a well-known problem of playing the bass. It's really hard to get the string going with the bow. Now, there are advocates for pure equal tension sets. I mean, really pure, exactly equal tension sets for the Baroque violin, from historical arguments, and for the modern guitar. I think I'll stay out of that debate, okay? There are some pros and cons to those views. The other comment I will make, about this comment about that feels comfortable play is that comfortable play is really determined by musical and playing styles, which have evolved with time. And so, as an example, modern violin string tensions, contrary to popular belief, are not high compared to historical string tensions. Modern violin string tensions are only high compared to what they were perhaps 50 years ago, but they are much, much lower than most historical gut string tensions were. So finally, let's examine damping. Damping is how quickly the vibrations die away. And so here are the major sources of damping. We have the internal damping of the string materials. The other major mechanism of damping is bending stiffness. And as Jim has pointed out to me, it's the damping due to bending stiffness is actually the same mechanism of damping as the internal damping above. And you can read all about it in one of his recent papers on his website that he co-authored with Nicholas Lynchard and about that. There are frictional losses to the core and the windings rubbing against each other. The problem with modeling frictional losses is that it's nonlinear. It's hard to model because it varies with amplitude. There's also added damping materials inside the string because we, as well as some other manufacturers, add additional damping materials into the string if we need more damping for boat strings. And that added damping material can dominate all the other sources of damping. There's also fingertip damping. You can hear that an open string sounds brighter than a stop string. This is most significant for the E string, which has very low damping. There's air damping due to the friction of the air as the string moves through the air. This is only significant, only mainly at the lower string modes. You can work out the equations for that and prove that and actually measure it. Radiation damping, that's the string actually radiating sound into the air. Well, it's fairly small because the string is a fairly inefficient radiator of sound because the dimensions are so small. And then you have instrument body vibrations and damping, which, although Jim didn't directly talk about this, a lot of his talk previously sort of alludes to this, but I think he left sort of the descriptions of the damping out because that would just add a layer of complications to his talk. But for the violin family, the damping or the losses when the string is mounted on the instrument, the losses due to the instrument vibrating is fairly small, except at the major resonances. And the most obvious example of that and the ill effects are the wolf notes that occur at major string resonances. For other instruments, the ratio between the string and body damping varies with the instrument and the frequency range within the instrument. And I know that Jim is working on research for this. The extreme examples for this is actually the banjo, where when you pluck a string on a banjo, the vibrations die away very quickly because the damping due to the instrument itself is so high compared to the string, unlike a violin. And so a lot of the energy in the vibration of the string is immediately transferred to the banjo and radiated out as sound through its membrane. Finally, I'm going to mention dead strings because the mixture of sweat, oil, and dirt and dead skin cells when you play the string makes a very effective damping material. And that's the major source of strings going dead. Some other effects are corrosion with time, and also with synthetic core strings, there's, I believe, a strain hardening effect with time for synthetic fibers. That is, the fibers actually get stiffer with time under loading. I'll just mention that we measure damping on a fixture with a big giant granite block, because if we didn't have a granite block, and I tried this without a granite block, we actually end up measuring the damping of the fixture itself rather than the string. So one of the main things is that the damping of bow strings is about an order of magnitude greater than the damping of guitar strings. Okay, and you can see this in this picture. Vertical axis is damping, horizontal axis is the frequency, both in logarithmic plots. And this is very typical. Pluck strings need very low damping because the only source of energy is the initial pluck. You don't want all that energy to die away inside the string. However, bow strings require much higher damping than pluck strings because there's a continuous source of energy fed into the string from the bow through the Helmholtz stick-slip mechanism. And there's a reciprocity principle in physics where resonance systems that take a long time to die away take a long time to get started up if they're excited by a continuous source of energy. So basically, low damp strings take too long to start up. The one exception is the plain steel violin E string. Even though it's got incredibly low damping, it seems to work fairly well. I think that's because the frequency is high enough that the amount of absolute time it takes to start the string is reasonable and has very low bending stiffness as well. So what are the practical effects of string damping? Increasing damping, you get a less bright sound, a duller sound, because for pluck strings, there's a faster decay of all of the partials, and so there's less total energy in that partial for the ear to perceive. And in the bowed string, the damping causes all the partials to lose energy at that partial, and so higher damped strings sound less bright. For plucked strings, there's also an overall sound, sense of shorter sustain with higher damping. And as I've just mentioned, higher damped strings generally are easier to bow. It reduces the time to Helmholtz motion. So let's look at typical damping numbers for orchestral strings. Well, on this plot, I'm not sure that there's anything really useful to be discerned. It's just that we see, because the frequency ranges are very different. And both of these, the damping and the frequencies, are plotted on a logarithmic plot. But if we plot the damping as a function of the partial number, which is what we typically do, I typically do, we get this plot. Okay, so the damping ratio now is plotted on a linear scale, and the frequency is all normalized to the partial or harmonic number of the string, irrespective of the actual absolute amplitude. And what we see is there's a pattern. We find that it doesn't matter whether it's a bass string or a violin string, the acceptable range for most bow strings fall in this sort of gray area. Strings that lie around here tend to sound bright on the bright side. And if they lie over here with higher damping, they tend to sound duller. And if they're outside in this region, they're generally too dull for bowing. And if it lies outside in this region with much less damping than this, they're too bright for bowing, and you're starting to get into the realm of guitar strings. So this is, with a little reflection, does make sense, because it turns out that the damping, the way we define damping, is a ratio of how much energy is lost per cycle of vibration. And therefore, there's already built-in scaling factor to account for frequency when we plot the damping as the partial number. And as I've mentioned before, we can add different amounts of damping material inside the string to adjust the damping, and we do, depending on the exact results we want. So The main points are that the string tension does affect the bowing and plucking response. The string damping affects the sound and bowing response. The string bending stiffness affects the bowing response, makes it harder to bow, and for plucked strings, it increases the damping. And that's actually why we wind strings, is to reduce the bending stiffness. And finally, the main message is that we string manufacturers, we make a wide variety of range of strings to choose from. So with different performance characteristics, using different combinations of materials. So there's a huge variety nowadays to choose from. And I would say that the problem actually is that there are so many strings out there that for the average maker or player, it's very confusing to figure out which strings are best, and which I didn't cover in this talk. So that's my talk, and open to questions. Any questions out there? Oh. Claudia.
Yes, thank you very much for your talk. I just had a quick question, because at some point you said that the damping of the string is higher than the damping of the body. And I thought it would be the opposite, because
did I misspeak?
Sorry?
Wait a minute. The higher damping of the string is higher. I might have misspoken. I probably meant the other way around.
Yeah, you wrote for the violin family that the instrument body damping is small compared to string damping, and it's the opposite.
Yeah, I think I misspoke. Yes, thank you very much for the correction.
Fan, can I just? I think what Fan was talking about then, it's the string damping due to the body coupling, which is small compared with the string damping due to intrinsic damping.
Ah.
He wasn't talking about body damping. It's the effect on the strings of the body, and that's smaller than you might think.
Okay, that makes sense. Thanks.
Oops.
It's my turn then. I have two questions. One is related to the former one. Does the bow hair damp the strings as well? You're muted, Fan. You're muted.
Oh yes. How did it? Okay. Am I unmuted now? So I don't know. I'm going to have to defer that question to somebody else. Anybody want to take a shot at that?
I'll give you, well, there's a trivial answer, which is that, yes, it could be. I mean, if you think of resting the bow on the strings and then doing a pizzicato, do you hear more damping? Sure you do. You hear other things as well. So but for normal bowing, it's a rather misleading question, because the bow is part of the excitation mechanism. So the string is not moving. I mean, there is energy loss during the slipping phase of the Helmholtz motion, for sure. And that's part of the energy budget. But it doesn't really come in the damping that Fan was talking about. I don't think that's a contribution to these effects of the minimum bow force and the length of starting transients and so on, because any calculation of a bowing transient is already factoring in the effect of the bow being there, probably.
Okay.
And second question?
Yes, it was how much decibel output from the instrument can you expect to gain from the upper and the very lowest type of string? What is the gap, the range you can get out of a typical string set from strong to weak?
Is your question the differences between
The sound output? I'm thinking about because it's different tensions and different
is your
tensions.
question like the difference between a heavy tension or a light tension set?
Yeah. Yes, right.
Okay, so the differences between, let's say, medium and light and heavy depends on the set and the manufacturer, but they're typically, you know, between 5 to 15% difference in that range. Okay, so
Do you know what it is in decibels?
well, everything else being equal, but they're not. Okay, if under the identical bowing conditions, then if you have 10% more force, you can, you know, calculate what that would be equivalent in decibels. Okay, so but there's a little subtlety to that, in that, well, number one, you don't necessarily will use the string and bow it identically if it's a different tension. And then there's another subtle effect, which that so typically heavy tension strings will sound louder. You know, they will sound louder under the identical bowing conditions. But it turns out that if you look at the shell end diagram, light tension strings can be bowed closer to the bridge, which can make up for part of that. And here's the most important thing, actually, which is that psychoacoustically, the perception of loudness is not really dependent primarily on the strength of the fundamental. It's dependent on the amplitude of the higher partials. In time or spatial terms, it's dependent on the sharpness of the sawtooth, okay? And that is highly dependent on bowing conditions of bow force and bow speed, and indirectly affected by the sounding point, because the sounding point determines the maximum bow force you can use.
Okay, difficult. Thank you.
George?
Yeah, I was going to ask this question because it looked like nobody else is going to speak, but just one little point about the twisting of strings for historic instruments. The very high twist string also has very high rotational stiffness as well. So in fact, you think perhaps the thick gut string would have a problem with torsional modes, but they don't, because the high twist compensates for that.
Yes, thank you for pointing that out, George. And I would say the modern analogy of that is that if you look at stranded steel core strings, if you have very short lay, tightly twisted stranded steel core strings, that uses the same principle that you try to reduce the bending stiffness of the core for fairly large cores for cello and bass strings, and still have high torsional stiffness.
Those, particularly for something like a cello C, stranded core is way superior to a solid steel core.
Yes, that's right, for that reason. Yep, exactly.
Yeah.
So you can say that there's really no new tricks under the sun, that we've just merely reinvented an old technique.
But quite difficult to deploy, say, for a floss synthetic core type of string.
Yes, that's correct.
Practical to do with a stranded steel core.
Yeah. Mm-hmm.
I mean, well, just one other point is in historic instruments, I think sometimes people assume that the things that make strings false are lack of uniformity in diameter. But in my opinion, it's actually every bit as much lack of uniformity in bending stiffness.
Oh, okay.
The strings.
That's good to know.
So a string, if it was made out of very similar strands, it may vary in diameter a bit according to the way they're packed together, but the mass may not be very different, of course. But certainly a string that's not very highly twisted can have quite a lot of variation in bending stiffness as you go along its length. And one way to tell is if you take a string and start to move it, try to wrap it in a circle. If you can make a circle with it, then it's got uniform bending stiffness. And if it goes in lumps, then it's got differences.
Thank you, George. For those of you who don't know, George Stepani, in addition to a wonderful violin maker and co-author of modal analysis software, is an expert on gut strings. George, you.
Hi, everybody. Fan, I've got a question for you about damping. And quite some time ago, we were talking about plucking open strings on a violin and comparing that to a guitar. Well, what happens then if you've got an instrument that seems to be a violin, for example, that seems to be pretty resonant when you pluck it? Is that a hint that the violin is going to be too bright for bowing?
Oh, okay, we're short of time, so I'm sort of going to duck this question. That's sort of a completely different question, because when you're plucking an open string and you're actually listening not just to the string itself, but the way it's exciting the instrument itself, and trying to discern if what you hear has any relationship to how you think the instrument will sound under bowing.
Yeah.
That's the question. That's too big to chew, to address in this forum. And I couldn't answer it even if I had time. That's a short answer. Andrew.
Hey there. My question is about, I'm interested in equal tension, the rise, the sort of, the rise of unequal tension from equal tension, especially the E string. So what's the thinnest? Is it practically possible to make an E string that is in equal tension, that isn't thin or wobbly, or has it ever existed in equal?
So
tension
okay,
E string?
so the part of the talk that probably I got totally screwed up on was that E string part, and I was thinking, wait a minute, I might have explained this completely wrong. So
I liked your explanation, was very nice about impedance.
Yeah, but what one is talking about, so it turns out for the violin E string, you can make very high tension violin E strings with gut, as George can tell you. Okay, yes. So that's not the problem, because it turns out that the stress loading on a monofilament is uniquely determined by the length and the frequency. It's not determined by the string tension or the diameter of the string. Okay.
Right.
What I was trying to say in that thing, though, for viola and cello, where the string is wound, you've used part of your mass budget on the winding, which doesn't contribute to the strength of the string, and so your core becomes very small. And there, it is important that if you can have higher strength materials, for the core to be able to use higher tension strings, to be able to put more of it into the windings. Because for viola and cello, if you use solid steel, it, for most people, is way too bright. We're okay with it for violin, but typically not okay using plain steel E string for cello, because it sounds way too bright.
Right. My question is about violin E strings, but obviously you can wind a gut string up to high tension, but can you create a low tension steel E string that is unwound, that is just a plain steel E string?
We use them. Well, but if you use a really small diameter plain steel E string for the violin, you'll find that it's not what you want.
So the answer is no, because the diameter becomes too small.
No, it'll work fine, but it's not what we expect. I mean, from a physical point of view, it works perfectly
Right.
fine.
Right,
Okay.
but
It
it's
sounds too
uncomfortable.
soft. It just sounds too
uncomfortable
soft.
to play.
You can't play it loudly enough because the
Okay.
string, yeah. So one last question from Sabine. We have to get on to Joseph.
Thanks.
Oh, you're muted.
Sorry, could you reiterate all the functions of the winding?
Repeat that.
Repeat what all the functions are for the winding of the string.
Yeah, basically
what's
we
the
wind
winding?
strings so that it's more flexible. And
Okay.
and if you need a lot of mass to add a lot of mass for the lower strings, then if you just use one winding, the bending stiffness could be way too high. So we often use multiple windings to keep the string still flexible. Another, which I didn't mention, reason for multiple windings is that the more windings you use, the more frictional losses there are. So there's a role there in terms of trying to increase the damping with frictional losses. A lot of this, I sort of glossed over because we don't have really good quantitative data on the exact proportion of frictional losses versus bending losses and all that stuff. It's hard to tease out the individual contributions of all of these individual mechanisms. So string design is still predominantly somewhat of an art. There's certain things we measure and calculate very well, like string tension, but other things not so well. We can measure damping very well, but to try to predict damping for wound strings is much more difficult. So with that,